Okay, so everything I've just said is of no value, but anyway, so does that kind of answer your question there, Craig, a little bit?
Yeah, that was really helpful. Thank you.
Yeah, okay, good. And now what we may see is, because now that everybody's using power electronics, I wonder if we don't go back to combiner boxes, because then why not save money on your wiring if the MPPT is handled at the panel level, not at the inverter level? So that may be something that we're going to see in the evolution of all of this, as all the different panel or all the different things begin to morph and evolve, and who knows, once artificial intelligence is put into the system, our robot overlords will come up with a different system for us. Anybody else have any quick questions on that? All right, so let me hit a couple of things I wanted, a real quick announcement, because we're coming up on the end of all of this. For everybody except the Marietta group, you've got one more week of these weekly sessions. And then for the Marietta group, we'll be meeting at 622 8th Street in Marietta. Since we've got a very small group, I thought rather than going into Marietta College and trying to deal with the security there and trying to get cops to open up the building over the weekend, we just hold it here at our office. So that's what we'll do. I'll send a note. There are only two folks I don't know that I see. Craig, were you one of the Mariettas, or are you somewhere else?
I am West Virginia at the moment.
Oh, okay, that's right. You're in Dayton or Indiana or whatever.
Indiana, yeah,
Yeah,
Indianapolis.
and you're coming to West Virginia.
That's right.
Yeah, you have the option of Hiram as well, so that's
Okay.
up to you, or Marietta if you want to come
Okay.
this
Yeah.
weekend. So that'll if you're coming this weekend, let me know, because
Marietta is this weekend.
yeah, Marietta is
Okay.
this weekend.
Okay.
So
Yeah, I won't be coming. Yeah.
okay.
Okay.
All right, so you're either Hiram or West Virginia, but I've got you down for West Virginia at the moment.
Good. Okay.
All right, so we're looking at West Virginia this weekend, and I'll send details to the two students who are coming for that. So at this point, you really should have gotten through chapter 7. That's kind of where we all should be at the moment. And a little bit of good news when it comes, I want you to get through all the chapters, but when it comes to the exam, you'll only be tested on chapters 1 through 8. So 9, 10, 11, those are short chapters anyway, but they're not part of the ETA examination. But I do want you to get through them anyway, so that your online course shows that you finished it all up. So as far as preparation for next week, in this review, we'll talk about chapter 8 and 9 and 10, 11, if, just touch on them. But then you should be all set, because next week is West Virginia, right? Thursday and Friday of next week, or 9, 10 days from now. And then Hiram is going to be in early October, the weekend, October, I forget, 10th and 11th, something like that. Okay.
It's the 7th and 8th.
7th and 8th. Okay. Yeah. Whatever the
Sorry.
weekend is. I'm so discombobulated when it comes to time. So hopefully I know you're students, but you should still know when a Saturday and Sunday is, right? So, although Hiram's not the kind of party school I went to, like at OU. So, or at least maybe you're more subtle about it than we were at OU. Okay, so let's I thought what we would do here, because chapter 7 is really when we get into the meat and potatoes of calculation. And oftentimes this is when people have real concerns or issues, start to feel confused by the material. In the list that I send you, there are some videos that walk through some of these design problems. So I'd encourage you to go through that. But I thought I would touch ask you guys, those of you who showed up here, if there is a kind of problem you'd like me to work through, something specifically that you're having issues with, like string calculations, or the battery bank sizing, or an array sizing. Those are kind of the things I'm focused on at the moment. Anybody have something that came up in your study that just left you confused?
The configuration worksheet I found to be really helpful for the grid tied array, but there wasn't such a worksheet for the standalone array, and I assume it's because it's more direct. But I also struggled with how many panels we needed on the standalone. So those are my questions. But
Yeah, and the standalone is how many panels do you need? That gets a little bit confusing, and you won't be asked specifically that on the test, but just for your own comprehension of it. With a grid tied system, you're really talking about averages, because the grid evens out disparity at different times of day and different times of year. So when you size a grid tied array, you're sizing it based on your annual consumption of electricity, and then how much power will be produced over the course of the year. Some months you're going to generate a lot more power than you're using, and some months you're going to use more power than you're producing. But at the end of the year, it all evens out. That's kind of the philosophy behind grid tied systems. Standalone systems, you don't have that luxury, because you have no grid to even things out. So that's when you usually start looking at critical month. And so that's where in the book, we're looking at finding out, you sort of plot it out based on how much power you're generating and how much power you're using. And then if you plot them month by month by month, you're going to find the month where it's the worst. And it's usually going to be a month like December or January here in the Northern Hemisphere. And then you size your array based on that month. So rather than looking at annual averages, you look at monthly worst case scenarios. So if you've done that kind of plotting, and I forget where in the book that is, but you should be able to find it, where there's a little bit of a table, and I know you do a coefficient type thing, and you figure out, okay, the critical month is August, or the critical month is, January. And then you just size it according to that. So let's see if I can do a little example off the top of my head. I'll go back to the screen share with the whiteboard. All right, so got to figure out how to get down here to the bottom. All right, so let's just throw out some numbers. I know, Craig, you were talking about your dad's house down in Puerto Rico. Let's just say that, how big of a house is it? Do you know?
First of all, it's my father-in-law, and I think the house is about maybe 1,500 square feet, maybe 1,000. So I'm not really sure exact size. And there's no real address there. He lives on the second mountain. Kilometer 44.6. It's like
right.
I don't know. I could find this on Google Earth if I tried. Yeah.
Is it a typical suburban home, or is it more like a cabin?
It's like a typical Puerto Rican home, but it's on like a big piece of land.
Okay. Does he have air conditioning and things like
that? But it's window unit. It's not central.
Yeah. Okay. So let's just throw a number and say that his monthly electric bill, kilowatts used, let's just say 600.
Yeah, that's probably about right.
kilowatt hours a month. But it's not going to be 600 every single month. So if we throw some things like, you know, in the summertime, it's, let's just do it real simple. The 3 months of the summer when he's using air conditioner, you know, window units, 600. Then we've got shoulder of 500. And then let's say in the winter time, he does a little bit more, 550, because there's some heating going on or something. And then we have 500. All right. So these would be our monthly. It's very hunt and peck there. So this would be our month. This would be June, say. And
Yeah.
now we start looking at solar insolation. And if we look at the insolation, how many hours of sunlight and the like, we're going to see a lot better production in the summertime and a lot less production in the wintertime. So I would assume with this kind of numbers, let's say in the summertime, we're looking at, say, 7 hours of insolation. These are not, we would do it legitimately. We go to PV watts and all of that. And then we'll just, for simplicity's sake, say these are 6 hours. And here's 6 hours. And then these are going to be 5 hours. All right. So easily we would find that our worst case month is going to be here, 5 hours of insolation. And there's a way that we would figure it all out. But I know that the ratio here. So I'm going to design this system so that in a typical month, our daily load is going to be this divided by 30.5. So let me find a calculator here. It's always problematic when I do these things off the top of my head. Divided by 30.5. So our daily load's 1.8. Does that sound right?
Yeah.
1.8 kilowatt hours per day. And we have 5 hours per day. So 1.8 divided by, it's actually going to be 1800 watts divided by 5, 360. Is that right? Is that telling me I need 360 watt hours each day? Or watts, sorry. 360 watt array.
Well, I was thinking there was 360 watts. Yeah, that's a good point. I don't know. You divided by 5 hours because we have 5 hours of insulation.
Yeah, this is bad. I'm trying to do it backwards. Tell you what. Oops, sorry. I hit the wrong button. That's always good. Yeah, I'm going to confuse you guys if I just try and do it this way. I'll confuse myself for sure. Let's just do it normally. All right, so how do we figure out a solar array? Typically, the size of an array will normally take, what is the monthly, the daily load? Is that right? Yeah, the daily load. So in this case, if I've got a typical 800, or we said yours was 600, right? 600 kilowatt hours per month. Divide that by 30.5 days. And that's going to give us our daily load, right? So let's make sure I don't miss a decimal. So 600,000 watts divided by 30.5 days gives me 19.672 kilowatt hours per day. And then if we say, all right, Our hours per day is going to be 5. Now we divide this by 5 and I get a 3,934 watt array, right? If it's working at 100%. So nothing works at 100%. And if this is so we have to derate it. So what do we derate it by? Well, now it's derated by whatever the efficiency of the system is. A standalone system. So what are some of the derating factors? Well, there's the inverter inefficiency. So that's always one of the big ones. So now we have to look at the inverter that you're using. Let's assume this is a N-phase system. Probably wouldn't be, but yeah, let's just say, okay, we'll do a regular SolarEdge with a battery backup system. All right, so the efficiency is going to be 98%. So I'm going to put 2% for inverter. I'm going to put 2% voltage drop. So those are two that are going to be popping out at us right away. Then I usually like to add 1% just for miscellaneous stuff, connections, things like that. Just throwing them out there. With the optimizers, if this is an optimizer system, there's going to be another 1% because they're not 100% efficient. Now, if there's a battery system in here, I think their battery systems for one of these is in the neighborhood of 5% loss internally within the batteries. So let's just assume we've derated it at this point and we're 11% derate. You can add in some other derates. For example, they typically like to add in soiling. You know, if you're in a dusty environment, the panels get dirty. I might lose 2 or 3% on average. Especially that might be true if this is along a gravel road where every car that drives by kicks up dust. You can get downtime. Like if you think you're going to be repairing it periodically, they'll sometimes put in there. You'll do the plus or minus if it's a string inverter kind of thing. So let's just derate it at 11%. So derating at 11%, we'll take this. If it's 11% inefficient, that means it's 89% efficient. So I divide 3934 divided by 0.89, and we get 4420. Is that right? Yep. 4.42 kW array. Okay, so that's how you would size either a grid-tied array or a standalone array, right? Because it doesn't really matter. The only difference is with a grid-tied array, you're sizing it based on annual averages, and on a standalone array, you're sizing it based on the worst case month. Okay. So, and in the worst case month, you would say, what is, you know, how much sunlight do I have and what are my load demands? You know, so it's whenever those match. Because if you have lower sun and lower load demands, that may not be the worst case month. You know, you're looking at that ratio, the ratio between available sunlight and load demand. That's going to be your worst case scenario. So, all right. So have I confused people with how you size an array? It's pretty straightforward. Now what you need to know is how many panels do you need, right?
Right.
So in a case like this, well, 4.42 kW array is pretty small. So maybe I go out and buy myself, 380 watt panels. Well, then it looks like it's going to be in the neighborhood 11 or 12 or so, right? So 4420 divided by 380. Yeah, 11.63. So I need 12 panels. right? So how
Yeah.
would I configure these? Well, I already said with Solar Edge, if it's a Solar Edge system, you're going to look up the specs, and Solar Edge is going to tell you how many are allowed to be connected in a string. So in this case, let's jump into which one is my, trying to see just if I've got one open. I do somewhere. Is that the one? No. Trying to see where I've got I think I want to jump in and might pick the wrong screen here. Yep, I knew I was going to. Screen sharing is stop. Share screen. There we go. That's the right one. Okay. Can you see when it says email campaigns or whatever? So So I'm just looking online for a Solar Edge spec sheet because I'd have to Solar Edge optimizer. Here we go. This will give me just an example. So, all right. Do they have a spec sheet here? There we are. All right. So this is showing me it's a 25-year warranty. Notice there are 320s, 340s, 370s, 400s. So that's how many watts these operate under. We said we're buying 380 panels. So we'd need to have probably a 400, P400. We could do the 405, 505. And somewhere along here, it's going to say how many optimizers in a string. So this is showing me the minimum string length is for the 400 is 8. So I've got to have 8 panels hooked together in a string with these optimizers. Otherwise, it's not going to work. And the maximum is 25. So there are no string calculations when you're dealing with Solar Edge. You're just going to look at the spec sheet, and based on the unit that you selected, it's telling me 8 and 25. So our design was 12, right? 12 panels. So I only need one string of 12. But if I come up with a system that had 30 panels, now I'm going to have 2 strings. 2 strings there. And I would likely design it 2 strings of 15 just because they're balanced. But in this case, they don't have to be balanced. It could be 1 string of 25 and 1 string of 5. And you might do that if you're thinking you're going to expand this in the future. So that's one consideration. That's one of the nice things about designing using Solar Edge. No string calculations. Remember, you didn't have to do temperature adjustments. With microinverters, you're just dealing with one inverter, one panel. So that's really simple. But with the Solar Edge, you've got that. Now with the other string inverters, and what you're going to have to deal with on the test is how many are going to be in a string if you're dealing with a standard old-fashioned string inverter. Well, in this case, how do we deal with that math? Where do we start? Where do we start when we're trying to figure out what is the maximum number of panels I can have in a string and not exceed the voltage limitations of my inverter? That's basically what you're worried about. When you're dealing with these string length calculations, you're trying to make sure you don't exceed the maximum voltage and you have enough to get the thing functioning. So the minimums are based on what is the minimum startup voltage of the inverter, and the maximums are what are the limitations. Typically in the United States with a residential system, we're going to limit ourselves to 600 volts because that's what the National Electrical Code says is the maximum voltage for a residential system. But not all string inverters go to the full 600 volts. Some of them cap off at 550. Might be another one that's 500. So don't assume it's 600 volts just because you're doing a residential system. You've got to look at the spec sheet of the inverter and it'll tell you what's the minimum startup voltage and what is the maximum operating voltage. It'll be right there in the spec sheet. So let's say we've decided we've got an inverter and our inverter is start up at 100 volts and it'll go to 600 volts. So that's one thing that we're dealing with there. Now, what are we, so normally if I said, all right, this panel operates at, let's say my panel has an ISC of, that's not going to be right. Let's say 30.8 volts is my ISC and my IMP is 28.1 volts. All right. So you would get that from your panel spec. I'm just making up numbers and I hope this is going to work out. But so how many panels could I hook together in a string and not exceed 600 volts? Well, normally you might just go, well, 600 volts divided by worst case scenario, 30.8 volts. And that gives me a number, 600 divided by 30.8. And that's going to give me 19, right? So I can hook up 19 panels in a string. Well, not really.
Yeah, just a follow-up question on that. The 600 volt limitation that comes into a residential system, is that per string? Is that what that is? Or is that
That's
per array?
That's going to be per string.
Okay. That's
Yeah.
right. 'Cause the book suggested that, but I always thought it was per array. That's what sort of threw me. So, okay.
No, because you can have multiple strings coming into the inverter.
Okay.
And then it makes a parallel connection within the inverter, which would mean that, of course, that the watt rating of your inverter is going to be higher. You know, like so if it just was a single string at 600 volts, well, 600 volts, 240. That's not going to tell you anything. I'm going off in a direction there. I don't need to. All right. So this would be your 19 panels if we didn't have to factor in temperature. But we do have to factor in temperature because we know that the colder it gets, the more voltage this thing is going to produce. The 30.8 volts is simply a rating at standard test conditions. Well, what is standard test conditions? Standard test conditions is 25 degrees Celsius, right? So what I have to do is at the location that I'm installing this, I have to know what the coldest temperature is that that site has ever experienced. So let's say that we're installing this in Cleveland, Ohio, for example, and I look online and I find out that the coldest temperature ever experienced in Cleveland, Ohio is, let's just say, minus 25 degrees Fahrenheit. All right. That might be the coldest ever. And if we convert that over to Celsius, I'm going to take a wild guess, minus 20 degrees Celsius. When you get into the negatives, they're pretty close, right in that range. All right. So what I'm trying to figure out is, what is the delta, the difference between standard test conditions and the coldest temperature ever experienced on that site. Standard test conditions is 25 degrees. And we then subtract a negative 20. So we end up with a delta of 45 degrees Celsius. Everybody see how that works? The delta is basically, if we have a continuum and 0 is here, 25 degrees is here, minus 20 is here, and the difference between them is 45 degrees Celsius. All right. So it's 45 degrees Celsius. So now what I have to do is I have to look at the spec sheet. So, and I've just been making up numbers. I may as well continue to make up numbers on this. But on the spec sheet of our solar panel, we go and we find out that at VOC, this panel has a temperature coefficient of plus or minus 0.36% per degree Celsius. So it's going to be written out something like that, right? And basically what this is saying is, for every degree Celsius it changes off of standard test conditions, the panel will produce less if it's getting hotter, or more if it's getting colder voltage. Well, how much less? 0.3%, 0.36% less for every degree. All right. So I know how much per degree, and I also know how many degrees variance. So I take that, and now I take 0.36 times 45, and I find out it's going to be 16.2%. Well, how do I know it's 16.2%? Well, first off, the degrees Celsius, per degree Celsius and degrees Celsius cancel out here because it's per. So now I've got 0.36% times 45. And so it's still going to be percentage. So I now know, because it's colder, this panel is going to produce 16.2% more volts than it would under standard test conditions. So what is it produce at standard test conditions? Well, I got that off the spec sheet. It's 30.8. So I take 30.8 volts times, and it's 16.12% more. So it's going to be 116.2%, right? Because it's going to produce 100%, but now I'm adding 16% to it. Well, if I want to convert percentages to a decimal, I just divide by 100, and it's 1.62. Everybody see that? Percentages converted to a decimal, you just divide by 100. So now I know that on the coldest day ever, this panel is now going to produce 30.8 times 1.162. So 35.79 volts. Okay. So on the coldest day ever, it's not going to produce 30.8, it's going to produce 35.79. So that's what I have to factor in. So now I take 600 volts, which is my maximum voltage, divide it by 35.79, and I get 16.76. Right? I don't want to exceed it, so I have to round down. This is telling me what's the maximum I can do in a string. So it's going to be 16 panels maximum. Did everybody follow that? That's how you do a string calculation for how many panels in a string for an old-fashioned string inverter. I see people looking at it and plugging away. Do you want me to leave that up for just a second? Okay. All right. So as you're looking at that and comprehending that, so basically, again, I want to give you the logic behind it, because I think maybe it was Nathan, you asked me about, or somebody asked me, how do we memorize equations for this exam? Well, the only equations we have to memorize are watts equals amps times volts, right? The power equation. Ohm's law, which is volts equals amps times resistance, or VER. And then voltage drop equation, which is voltage drop. It's just a variation on Ohm's law, right? Adjusted for distance. So voltage drop equals amps times resistance times twice the distance divided by 1,000 feet. So if Ohm's law is V equals I times R, volts equals amps times resistance, voltage drop is amps times resistance times twice the distance divided by 1,000 feet. Well, why did I have to make that adjustment? It's because resistance is given to us for the wire in the National Electrical Code in ohms per 1,000 feet. So what we're trying to figure out is how much loss do we have over this wire? Well, what portion of 1,000 feet are we dealing with? Because I know, for example, number 10, AWG stranded copper has, I think it's 1.24 ohms of loss per 1,000 feet. So if I want to know what my resistance is, well, now I got to know how many thousand feet I'm dealing with. Is it half of 1,000 feet, 500 feet? Is it 2,000 feet? Because the ohms are linear, right? The loss is linear. So it's proportional. So because that's where I get my resistance from, based on per 1,000 feet. Why is it twice the distance? Is because it's a circuit. So if there's a piece of wire that's going from point A to point B, and it's 180 feet apart, there are actually 360 feet of wire in that circuit, because there's a hot and a neutral if it's AC, or there's a positive and a negative if it's DC, and the electron is traveling over both of those wires, there and back. So twice the distance. So in this example for voltage drop, where do I get my amps? Well, for each string, by its very definition, when I hook things together in series, amps remain the same. So whatever the amps were for one panel is going to be the amps for the whole string. So if I look and I see that I put ISC and IMP. I probably confused people. That should have been VOC and VMP, because I was dealing in voltage. Now I'm dealing in amps. So I would look at the IMP, which is the actual amperage that this thing would be operating at. And let's say my panel, I look at that and it's operating at 8.6 amps. So now my amps are going to be 8.6. And if I look at my resistance, well, if I'm using number 10 cable, and I'll use that just as an example because I remember it, the resistance is 1.24 ohms per 1,000 feet. Well, what's my distance? Well, let's say it's 180 feet. So twice the distance is going to be 360 feet divided by 1,000 feet, or 0.36. Very simple there, right? That's why I put the 1,000 feet over here on distance and not on the resistance. Okay, so now if I just multiply that out, 8.6 times 1.24 times 0.36, and I get 3.83 or 3.84 volts, right? So what's my voltage drop? 3.84. I'm losing 3.84 volts going from this place to that place over that 180 feet. Is that acceptable? Well, now there are several things I gotta know. What's the voltage of my system? Right? This is why we keep wanting to push the voltage up as high as possible. Is because if this is a 12-volt system, like a standalone system that you're like, Craig, when you do the system for your father-in-law and you put together a solar generator and it's going to be 12 volts, for example. Well, if this system were 12 volts, I just lost 30% of all of my power, because 3.84 volts out of 12, that's like 30% of my power. The system's just not going to work. It's not feasible. But if it's a 600 volt system, a grid connected system, well, then it's going to be what, a little more than half of a percentage. Is that right? 3.84 divided by 600. Yeah, it's like 0.64%, less than 1%. Is that acceptable? Yeah, because we want to keep our voltage drop below 2%. Remember, though, these things add up. So every section of wire in your system, you've got to measure what the voltage drop is. And when you add them all up together, you want it to be below 2%. So how do you deal with that voltage drop? How do you lower it? Well, several ways. You can shorten the distance of your runs. You can use bigger wire, because the bigger the wire, the less the resistance in that wire. Or you can increase the voltage of the system. So those are kind of the three ways we typically deal with it. As a designer, you should try and make your distances as short as possible anyway. That's going to save money. It's just better design. So what is your normal solution? It's put in bigger wire. Put in as big a wire as you need. But higher voltage systems, for instance, in Europe, the systems are going to be around 1,000 volts. That's the minimum, or that's the maximum for residential systems. In the US, it would be great if we could operate at 1,000 volts. It would save a lot of money because we could have fewer strings, just as we calculated there. I don't need 2 strings. If I can go up to 1,000 volts, I could get by with 1 string. Well, that saved me money on wire. It saved me money on disconnects. It saved me money on breakers and fuses and all the other things that correspond with it. Saves a lot of money if you increase the volts, because what controls the size of the wire? It's amperage. The wire doesn't really care about the volts. Wire is manufactured to meet a certain voltage, but that's more about, we don't want power leaking out through the insulation. But so it's amps that are the big issue when it comes to wire. So why haven't we increased the voltage to 1,000 volts like Europe? Anybody have any idea?
NEC safety concerns.
NEC safety concerns. Well, they might claim that, although is 600 volts more dangerous or less dangerous than 1,000 volts? They're both going to kill you. I mean, after a certain voltage, you're dead. You know, I mean, so in fact, in many cases, people respect it a lot more and are a lot more careful. And a lot of times they always say it's the amps that kill you. Well, that's true to an extent, but it's really the combination of amps and volts. No, there's no inherent safety issue there. I think the reason why is because now who writes the NEC? It's basically written by the people who show up at the committee meetings. Who pays for people to show up at these committee meetings? Manufacturers. And the manufacturers have tooled up their systems based on 600 volts. And if you changed it, they got to retool their factories, redo their designs. It costs them money. So there's a real inertia. If there's a real reason for doing it, safety reason or something, yeah, they may overcome that inertia. But there is an inertia to leave things the way they are because people are always lobbying that they don't want to, have to pay out money. And yeah, you can sympathize with that. All right. So I've sort of wandered off into voltage drop here, but is everybody clear about voltage drop before I look at minimum sizing for this same example? Okay, I'm not hearing anything. So, all right, so we did maximum, right? We did maximum where we decided it's 16 panels max in this example. So how do we do minimum? What's the minimum startup? Well, we know the minimum startup here for your inverter is 100 volts. So we need to hook up strings where the voltage is enough to at least turn it on the hottest day of the year ever experienced in Cleveland, Ohio, in this example. So how do we do that? Well, now we've got to know not the coldest temperature, but what's the hottest temperature. So we look up online, and the hottest temperature ever experienced in Cleveland, Ohio, let's assume that is 43 degrees Celsius. Again, I'm just making up numbers, but I suspect that's, anybody know what 43 degrees Celsius is? It's probably in the 110 Fahrenheit range. I assume somebody's looking it up. All right, so if let's say 43 is the hottest, so what's the delta between these? The difference is 18 degrees, right? 18 degrees Celsius is our delta. Well, here's the one little trick on the minimum that's different than the maximum. It's hotter on a roof than it is ambient air temperature. So at this point, we have to remember that for ground-mounted systems, we add 25 degrees Celsius. For ballasted roof systems, we add 30 degrees Celsius. And for flush to roof mounted systems, we add 35 degrees Celsius. So let's assume this is a flush to roof mounted system. And a flush to roof is just one that follows the pitch of the roof. It's mounted, fixed mounted on a roof. So I'm going to add 35 degrees Celsius here. And now I've got a delta of 53 degrees Celsius. Okay. Everybody see that? All right. So now what do? That's the delta. That's how many degrees. So now we have to go back to our panel specs. And before we got the temperature coefficient. And it was the temperature coefficient at I think typically they say at VOC. So temperature coefficient at VOC. And that's where you'll find that one. But they'll also have a couple other temperature coefficients in the spec sheet. And oftentimes, if they don't have it at VMP, which is what you're really wanting to look for, they'll often have temperature coefficient at maximum power point, which is essentially the same as VMP. So we want to err on the low side. And this temperature coefficient is oftentimes, it's going to be different than the other temperature coefficient because you're starting at a different starting point. And I think if my memory serves, it's usually a little bit higher because the starting point's a little lower. So let's say that this temperature coefficient is plus or minus 0.405% per degree Celsius. So I got that from the panel specs. So I now know there's a delta of 53 degrees Celsius, a temperature coefficient. So I'm going to multiply that times 0.405% per degree Celsius. The degrees Celsiuses cancel out. So I get 53 times 0.405. So 21.46. 21.46%. So what is that telling me? On the coldest or on the hottest day ever, that panel is going to produce 21.46% less voltage than it would under standard test conditions. So now I'm going to take my, this was the VOC, but again, now I'm going to use VMP. So let's say the VMP is 28.1. I got that off of my spec sheet. So I take 28.1 volts, which is the VMP, times, and now it's 21.46%. So I'm going to say 100% minus 21.46%. That's going to give us 78.54%. Is that right? Did I do my math in my head properly? Or 0.7854. So now I'm going to take 28.1 times 0.7854, and it's telling me 22 volts. So on the hottest day ever, the panel is going to produce 22 volts. On the coldest day ever, the panel is going to produce 35.79 volts. Quite a difference in the amount. Well, I now know how many volts that panel is going to produce on the hottest day ever. What's my minimum startup? It's 100. 100 volts divided by 22 volts gives me, divided by 22, 4.54. But I need to exceed 100. So I'm going to round it up. So 5 panels minimum. So if you were answering questions on the test, you would find 16 panels maximum, 5 panels minimum. Or if you do SolarEdge, you can just look up in the table, which is a lot easier, right? It's another reason why people like SolarEdge and microinverters and things like that. I would say of all of the problems on the test, these type are the hardest. You know, they're the hardest to do the math on. And it really is just in your mind thinking through how things work. Why am I trying to get from this place to the next place? Okay. I look at the clock there and I see we're over our time. Anybody have any quick questions before we call it a day? Everybody's being so studious. All right. Okay. Well, I'll see you guys next Tuesday, except for the ones in Marietta. I'll see you on Saturday. And then the West Virginia people, I'll see you Tuesday, and then I'll see you next Thursday in West Virginia.
Hey,
All
Jay,
right,
one quick question.
Yeah.
For the workshops, we're not expected to bring any tools or supplies with us, correct?
No, we'll bring everything. Just wear comfortable clothing. So,
Thank
all
you.
right. Okay. Take care.
Bye.
See you guys. Bye-bye.